Okay. Oops. Oh, I just realized I'm not showing my whiteboard yet. Huh. Let me fix that. Okay. Yeah, I forgot to share it before I started. Okay. Uno momento. Okay. Right. Ah, there we go. Excellent. Okie dokie. Yeah. So, I did get an email with a question, so I will definitely look at that. But I think first carrying on from last time. So last time we were trying to derive this length contraction formula. And we sort of made a mistake somewhere. So let's go over that now again and try and sort that out. Okay. Okay. Viewer numbers seem to be really weird. They keep fluctuating a lot and only showing me when I click on users in chat. So I have no idea who's in the chat. But if you are in the chat, feel free to say hello. Okay. Hello, Theoretical Phys 77. Right, so the length contraction that we were talking about last time. I'm not alone. Oh, well, that's good to know. Thank you very much, SL1Y. Okay, so length contraction. Let's set it up like this. Good evening all. Good evening, Marmite Pasta. Let's choose the frame for this person A. And let's say we've got a beam or a log or something which is at rest in their frame. Okay. And then relative to that frame, we're going to have another observer that we'll call B. Oops, I didn't need to erase that, did I? And they're going to be moving to the right with a speed v. Okay, I'm going to unplug my iPad too because it's getting quite hot. So I think the issue last time, or something we should clarify from last time, is that when you're measuring the length of something, the length you measure for that thing is the space-time interval between the two ends at the point, or when you measure them simultaneously. Okay, so to measure the length of something, you have to measure both ends of that something simultaneously. Okay, and I mean that seems fairly obvious if something is still. You know, you can't put it on a little track moving along, and you have to measure where one is, and then you leave it moving off on the track, and come back a while later and measure where the other end is. You have to measure these things simultaneously to get a measure of the length. Okay. Hello, Machu D Pariah, I think. Hello. Okay. So in person A's frame, clearly you can see that this rod, it's stationary, and they can easily make a measurement of these two ends simultaneously, because the rod is staying still, so it's automatically, these two ends are simultaneous. But if we redraw person A's coordinate frame, and now I'm going to simplify the drawing slightly. I'm just going to draw the rod as this brown line on the x-axis, okay? And if we now draw person B's time and space axes on top of A's time and space axes, they will look like this. Okay. Where, as always, in space-time diagrams, this angle phi is given by tan phi is v. Oh, you like my video on GR? Oh, good. I'm glad. That was we've only done one thing on GR so far, which was this perihelion precession of Mercury. But hopefully we'll do some more GR stuff later. I'm glad you liked it though. Thank you very much. Okay. So let's see what is it that person B is trying to measure. If they're trying to measure the length of this rod, they have to measure the position of these two ends of the rod, but they have to measure them such that it's simultaneous in person B's frame. And because of the way that person B's axes are tilted, these are the lines of simultaneity in person B's frame. Okay, they're parallel to the XB axis. These are the lines that show a constant time coordinate. Okay, this line will have some time coordinate. This line here will have some different but still constant time coordinate. Okay, so the interval that this person has to measure, person B, is actually this length here. This is the length that they will measure, or this is the interval over which they will measure the ends of the rod simultaneously. So they have to figure out this length here. So if we compute the space-time interval of this highlighted length here in person A's frame, so I'm going to call this delta SA squared, well, that is equal to the spatial part of this interval. Remember, we're thinking about this at the moment, we're looking at this from A's perspective, in A's frame. So it's equal to this spatial length squared. And of course, this spatial length squared, remember the brown line represents the rod. This is just the rest length of the rod, okay? So I'm going to call this LA. This is the length of the rod measured in the frame in which the rod is at rest. So that's LA squared. But there is also a temporal component here. There is a slight difference between the time coordinates as measured by person A. So although these two lines are simultaneous in person B's frame, they're not simultaneous in person A's frame. Okay, so if we're looking for the space-time interval according to person A, we will have to include this temporal difference between these two. So remember, this angle here is given by phi. Phi is the angle. Tan of phi is v. So if you want to find this length here, which corresponds to the temporal distance between this axis and this point here, that is given by tan phi times LA, opposite over adjacent. So that is v times LA. And this is, of course, all squared. Okay. So that's from person A's perspective. Let's just rewrite that slightly. That gives us LA squared times 1 minus V squared. That is the space-time interval squared measured by A. Well, now let's think about what person B will measure. So person B measures the difference between these two red points simultaneously. These lie along one of these lines of simultaneity in B's coordinate system. So they measure no temporal distance between these points, but they will measure a spatial distance. And this spatial distance, remember, like we said, if you're trying to measure the length of something, measuring the length of an object corresponds to measuring the space-time interval when you make your two measurements of the lengths simultaneously. Okay, so they're measuring these two positions simultaneously. So this space-time interval for person B just corresponds to the length of the rod as person B would measure it. Okay, so we've calculated the interval between these two red points from person A's perspective here, and we've calculated the same interval from person B's perspective. And we know that in special relativity, this interval, as we've constructed it, is invariant. So delta SA, is equal to delta SB. Therefore, we can just equate these expressions here. Okay? And if we equate them and square root both sides, we get that LB is equal to square root of 1 minus v squared times LA. Okay, so this is this length contraction formula. So LB is the length measured by the person moving away from the rod. Now, it's symmetric, so I mean, we could also think of him moving towards the rod. He doesn't have to be moving away. This thing is symmetric in the direction of velocity. But the length that person B will measure when they're running towards this object, or equivalently when this object is running towards them, it doesn't matter, it's all about relative velocity, is reduced by this factor 1 minus v squared. Okay. So that is this length contraction result. If you saw like a spacecraft flying towards you at a significant fraction of the speed of light, then you would see the length of that spacecraft kind of squashed down. That is this phenomena of length contraction. And of course here what we've done is we've set everything to c. But if we wanted to put the c's back in, we might write this slightly differently. So we might also write it using a little soft l here, a lowercase l, which stands for the proper length, which does just correspond to this length a. It's the length measured in the reference frame where the rod is standing still. And if we put back in the factors of c we neglected, they appear in this way as a fraction of the velocity. Okay, so that's how we get that length contraction formula that we looked at last time. Then I got an email as well with 2 questions on. Where did that go? Where is that? Okay, so this person, the first question was about trying to estimate the max range of a Higgs exchange. Their reasoning is that using the lifetime before decay calculated from its decay width, it should travel approximately 10 to the minus 14 meters, not accounting for Lorentz contraction. However, using the uncertainty principle in a hand-wavy way from h bar over mc, I get 10 to the minus 18 meters. Is there a difference required in thinking about range of exchange and range before decay? And which would be the correct approach to finding an estimate for the maximal range a Higgs exchange can take place? Well, so I think in both of these you may have made a slight error in assumption. So if I'm correct, for the first one where you got something like 10 to the minus 14, you probably took the decay width of the Higgs boson, which is so the thing I find is that the total width is around 4 MeV. That's what I find for the decay width. So I'm assuming what you did. Oh right, yeah, 4 MeV-ish. Okay. So I'm assuming what you did is you converted that into a lifetime by doing h, or is it? I think it's h bar over the width. That gave you a time. So I mean, what is that? That's 6.63 times 10 to the minus 34 over 2 pi times 4 times 10 to the 6 times 1.6 times 10 to the minus 19, which is, well, it'll be about, what, like 10 to the minus 21 or so. So I get a decay time of about 1.65 times 10 to the minus 22 seconds. That's what you did. Oh, using natural units. Okay. So that's what I get for like the decay time of the Higgs boson. Then to get the 10 to the minus 14, I'm assuming that you then multiplied by c, right? By the speed of light. I mean, certainly if you multiply this by something 10 to the power of 8, you get a 10 to the minus 14. So I assume that's what you did. But I don't think that's a totally good thing to do, because the Higgs boson does have, you know, certainly non-negligible mass. It's a pretty heavy particle, actually. So saying that it will sort of travel at the speed of light, I think is not a good assumption to make. Unless I misunderstood what you did. But let me know. But I think possibly multiplying by c is not a good idea, because the Higgs boson is fairly heavy. It won't just travel at the speed of light. Yeah, I think it's I don't know what its velocity would be. I mean, its velocity presumably would depend on the kind of the incoming momentum of the events that produce it. You know, if it's on like an external leg, you know, its momenta will be determined by the things that produced it, but it won't just have velocity c. And then similarly, when you do this uncertainty principle argument, so when you use delta x delta p is around what do you use? Do you use h bar? Yeah, you use h bar. Is around h bar, or sometimes it's h bar over 2. I don't think it actually makes a difference. I think it should be h bar over 2, but it's a factor of a half in, you know, 10 to the minus 34. Oh yeah, there's the Discord. Thank you for clicking that. So you said you used h bar over mc to try and estimate sort of the uncertainty in the position, but again, you can't just use mc for the momentum here. So even if the particle was traveling at the speed of light, you can't just take its mass and times it by its velocity. You would have to use the sort of relativistic for momentum, which is like this. Okay, gamma mv. Yeah. So, or for a massless particle, then that for a massless particle, the momentum is mc. I suppose it's E over c. But the Higgs is definitely not massless. So I think you would have to. I'm not sure what you'd have to do. Maybe there's some way you could look up the energies of the things that produce it, and therefore what you'd expect the momentum in a particular case to be. How do you estimate gamma? As in the width of the decay. As in gamma, as in small gamma. Well, you would have to know the momentum of the outcoming particle, and that would depend on the momentum of the incoming particles, and the particular interactions it was going under. I don't know a lot about this kind of phenomenology, I have to be honest. So I don't know about what kind of interactions actually produce Higgs particles. But I think even if I did know more about it, you would still need to know sort of the energy of the jets coming, not of the jets, the energy of the incoming particles. Why is P equal to MC? Oh yeah, sorry. I think I was getting a bit confused then. So for a massless particle, so for light, for example, P is equal to E over C. Yeah, it's not equal to MC. It's equal to gamma mv if it's a massive particle. Yeah, my bad, thank you. So to find the maximum range, perhaps you could estimate momentum to be relativistic, i.e. v equals c. Well, certainly, yeah, that would be, I suppose, the maximum range. But of course, it could never actually travel at the speed c, because it has mass. But I suppose Well, I don't know how feasible that is. I mean, why not 10 to the minus 7? Why 10 to sorry, why not 10 to the 7? Why 10 to the 8? Because I don't know if these things actually in practice can ever get that fast. Yeah, I really don't know. I guess you could as an estimate, 10 to the 8. It's at worst it's going to be two or three orders of magnitude off. So I mean, it's as a rough calculation, it's not bad to say that the speed will be around c or something. But yeah, I think it's fine to do it like that. I mean, this is still a ridiculously tiny length over which it decays. That 10 to the minus 14 is like 10,000 times smaller than the width of an atom. So that is a very tiny length over which it's decaying. So yeah, I guess it's not a bad estimate to just say t will have to be rather the length will have to be less than 1.65 times 10 to the minus 22 times c, which is around 10 to the minus 14, I think you said. Yeah. Oops. But then I think that's 10 to the minus 14 in the frame of the particle itself. And I mean, massless particles don't sort of decay in that way. So, if this particle was massless and it was propagating through that length, it would really get much, much further from the perspective of somebody else, because they would see that, the length of the particle that was massless, it's like they would see their length massively length contracted. So the length someone outside would see would really be a lot longer. But of course, I don't think that is the case here. And of course, thinking about massless particles in that way is not entirely helpful, because then all this contraction stuff, length contraction and proper time stuff, sort of breaks down, because you can't really go into the rest frame of a massless particle. Yeah, sorry, I can't be more help there. I think putting, your approach sounds reasonable, doing 10 to the minus 14. I'd say your approach for the first method, where you got 10 to the minus 14, is more reasonable than your second method, where you used h bar over mc. Because then, if you had a relativistic particle, its momentum would not be just mc. It would be gamma m v. So yeah, that's probably the one with the larger error I can see, but I don't know. I'm not entirely sure. Okay, but thank you very much. Then you had another question. So your other question was about group theory. So my group theory is very rusty, but we'll see how we get on. You say, oh, where's it gone? Ah, there it is. Okay. You're trying to find the character table of a simple permutation S3 group. Your notes have a worked example. It sets it up in the standard way with 3 irreducible representations of known dimensions 1, 1, and 2, and 3 classes of size 1, 2, and 3. Then it goes on to show that the invariant subgroup made from the first class and the second class and its corresponding factor group. Here you become confused. The number of irreducible representations is 2, and both must have dimension 1. The irreducible representation of the factor group must be 1, 1, and 1 minus 1. Why must the irreducible representations of the factor group be 1, 1, and 1 minus 1? How do I go from there in identifying one of the unknowns in the character table? So I don't know exactly what you mean by the invariant subgroup made from C1 plus C2. Do you mean like you're combining those two classes to make one? Because so usually when I've done this, when I've studied character tables, you make use of the fact that there are quite strong constraints on the dimensions of your representations. So if you have a group G, so we have all our group elements that are elements of some group G, and you have your irreducible representations of this group, then the sum over the dimensions of these different irreducible representations up to some maximum value, the sum over these dimensions squared, is equal to the order of the group. So the number of elements that are in the group, that's what the order is. And then there's another constraint which says that K, so here K is denoting the number of irreducible representations, that is equal to the number of conjugacy classes or equivalence classes. Okay. So my approach would be, if you, so here we're looking at, the group we're looking at is the permutations over the permutation group with 3 elements. So you would find the different conjugacy classes of this group. Then, well, first you would find the number of elements in the group, which I think will be 6 for this permutation group, this symmetric group. So you then know that the sum over the dimensions squared of all of your representations must be 6. You can then find the different conjugacy classes, however many you say there are 3 classes, three different conjugacy classes. So then you know K is 3. So then you know that the sum over the dimensions squared of all the representations must be 6. You know you always have one trivial representation. Yeah, exactly. Which is, the trivial, the identity class is a class with only the identity of the group in it. That's always in its own class. But then you have a trivial representation where just all of the group elements are mapped to 1. So that has dimension 1. So working it out, you've got, so say we've got 3 representations, because as you said, we've got 3 classes. So we've got representation 0, 1, and 2. This is the trivial representation, so where everything is just mapped to 1. Therefore, this, of course, has dimension 1, because everything is just a single number, number 1. So therefore, putting that into this dimensional constraint here, you can say that 1 plus dimension of R1, where this is a different representation, plus dimension of R2 is equal to 6. And therefore, dim R1 squared plus dim R2 squared is equal to 5. And of course, the dimensions of these representations are always integers. So that tells you one of them has got to be 2-dimensional, one of them has got to be 1-dimensional. That's the only integer solution to this thing. So we can choose dim of R1 to be 1 and dim of R2 to be 2. And that satisfies this dimensional constraint here. So if the representation is 1-dimensional, thinking about the characters, so the character of a representation, the character of a particular representation Ri is the trace of, hello Alan MD, is the trace of the representation matrices, or whatever they are, you know, some of them, these are just scalars, but let's say the trace of the representation matrices that make up of all of these group elements. So it's like the sum over the group elements. So all of the group elements within the group of was that my arm? Was what my arm? Alarm. I can't hear anything. Can anyone else hear an alarm? Unless it's the background music hit. I did turn it up slightly, so it might be a bit louder than usual. My mind has gone blank. What was I doing? We were finding... Oh, we were finding these characters. So the characters are the trace over the representation matrices. So like... Well, in fact, let's just write it as trace over these particular representation matrices. Okay. And of course, in the case where the representation is one-dimensional, like in the trivial representation or this one here, then the trace of that matrix, where it's, you know, a one-by-one matrix, is just the thing itself. Okay. So another important fact about these characters is that characters are class functions, which means that for any two objects that are in the same class, they will have the same character to them. Okay, and I'm not going to prove that because frankly I can't remember how you prove it, but we'll take that as a given. Okay. So we should figure out exactly what these different conjugacy classes are. So you've said that there are 3 of them, but I think we should try and work this all out rather than... Yeah, an equivalence conjugacy class is a kind of equivalence class. And these characters are constant on this particular equivalence class, okay, that we define using conjugates. So let's talk in general a little more about the group S3. So we can define S3 as all of these bijective maps which map the set 1, 2, 3, or the set with 3 objects, back onto itself. So they're bijections. Okay. And often the way people will write these permutations, they'll write them in a little bit of a funny way, which I personally always find a bit confusing. So when I do it, I have to go back and write them out explicitly. So let's think about the different elements there are in this group. So if we start off with 1, 2, and 3 ordered like this, well, our permutation, we can just write on this bottom row here what these different objects are mapped to, how they're rearranged, because we're basically just finding the different ways there are of permuting the numbers 1, 2, and 3. Okay, so we could, if we like, leave them all exactly the same. We don't rearrange them, we keep them as they are. And this would be the identity element of this group. Leaving everything the same, we would call the identity. Okay. And sometimes in sort of permutation, I think they call it cyclic notation, people will write that like this. So this just means 1 goes to 1 and it stays where it is. It just shows that you're not actually doing any permutation to this. Okay. Or we could have... Oh, so I should also be clear, this is not a matrix here. This is like the upper part is before we've done any permutation, the original order of things, and then the lower one is after we've done the permutation. Okay. So we could also have 1, 2, 3 to start off with, and then we could switch 2 and 1. This corresponds to another operation on these elements, another bijection. So in this one here, we are sending 1 to 2, and we're sending 2 to 1. So we often write this as 1, 2, where this notation means you take 1 going to 2, and then 2 goes back to 1, okay? And there are, we'll see as we go through, as we fill in this notation, that it makes some sense, okay? So I'm going to call this element G1. And G2, well, we could, again, start with 1, 2, 3, and we could then take, we could swap 1 and 3. So we could have 3, 2, 1. So now we've taken 1 to 3, and we've taken 3 to 1. So I write this as 1, 3, okay, using this cyclic notation. Then G3, I'm going to call swapping 2 and 3. So I keep 1 where it is, and now I've swapped 3 and 2. So now, to get it into this cyclic notation that I think people like to write it in, we're taking 2 going to 3, and then 3 is going to 2. So we write this in this particular notation as 2, 3. Okay? But it doesn't really matter. This notation is just for completeness to show this different way of writing permutations. What about G4? So G4, we could have, we've already sort of mixed up all the pairs we can. We've produced all these possible pairs of 1, 2, 1, 3, and 2, 3. So now we have to think about doing something to all 3 numbers rather than just to 2 numbers. So we can no longer keep, for example, 3 fixed here, or 2 fixed here, and 1 fixed here. So let's think about going, say, from 1, 2, 3 to 3, 2, 1. Okay. This corresponds to, well, this is not a cyclic permutation. Oh, sorry. Hang on. That's not right. Let's go 3, 1, 2. Okay. So now we've taken 1 to 3, we've taken 3 to 2, and we've taken 2 to 1. So we write that as 1, 3, 2. Okay. Where that means we've gone 1 to 3, then we've gone 3 to 2, and then 2 back round to 1. That's kind of the meaning of this funny comma colon notation. Well, just comma notation, there's no colon. Okay. And G5, the final permutation we could have, we start with 1, 2, 3, and then we can go to, well, what haven't we had? We could have 3, 2, 1, 2, 3, 1, like that. Okay, so now we've taken 1 to 2, 2 to 3, and 3 to 1. So we write that as 1, 2, 3 in this cyclic notation. Yeah, 2, 3, 1, exactly. Thank you. So these are our 6 elements. We've got the identity, which does nothing. We've got G1, which swaps 1 and 2. G2, which swaps 1 and 3. G3, which swaps 2 and 3. G4, which is taking 1 to 3, 3 to 2, and 2 to 1, and G5, which is taking 1 to 2, 2 to 3, and 3 to 1. Okay, so these are all of our possible permutations. Okay, and now I think to find the conjugacy classes can be quite a sort of long thing. Let's define the conjugacy classes. So 2 things, GI and GJ, are in the same conjugacy class if for some there exists some G in the group such that G times GI is equal to GJ times G. Okay, this defines the conjugacy class between GI and GJ. They're in the same conjugacy class if there exists some G such that this is true. Okay. And this kind of explains why E, the identity, is in its own conjugacy class. So we can call that C0. Because if you imagine you put E here, where Gi is, so say you're looking for the things that are in the same conjugacy class as Gi, what you would do is you would put the thing that you're looking for, whatever's sharing its conjugacy class, into where Gi is. So in this case, if we're looking for things that are in the conjugacy class, the same one as E, we put E into here, and then we would kind of run through all the other group elements, G, to see which elements will multiply in this way to give some different group element here. Okay. Hello, Bryce Allen. But for E, it should be fairly clear that if you put E into here, then the only other thing you can have here is also E. Okay, because if you put E into here, you'll get a G here. So then you end up with something like G is equal to GJG, and this is precisely the definition of the identity. So the identity is always in its own conjugacy class. You have a science and technology question. Oh, wonderful. Okay, sure. Feel free to type it out now, whatever you want to do. We're sort of in the middle of a little bit of a group theory shenanigans at the moment, so we'll have to finish that beforehand. But thank you. Then the other classes. So we're told in the question that Marmite Pasta sent that there are 3 conjugacy classes. So the remaining 5 elements will be divvied up in some way between these conjugacy classes. And I think they'll be divvied up because this actually, I think I did a problem sheet on this sometime last year. I think they're divvied up in this way. Hi, Doe is here. Nice to see you. I think the conjugacy classes are divvied up like this. So I think these are in their own conjugacy class. And I think these 2 here are in a separate conjugacy class. I don't know if that's what your notes say, Marmite Pasta, but as far as I know, that is correct. That is correct. Okay, all right then. Well, let's stick with that, because, like I say, in practice, what you would do is you would have to test all of these, or get a computer to test all of these. As far as I know, there's not a nice way to just sort of figure it out. Okay. So let's define the other 2 conjugacy classes. So the other one I'm going to say has got G1, G2, and G3 in it. And the second one has got G4 and G5 in it. Okay, so there are 3 of these classes. And what we know already, so because we have 3 classes, remember we had this, let me get rid of that. Don't know what that's doing down there. Okay. Because we had these 3 conjugacy classes, remember we had this equation that the number of representations was equal to the number of conjugacy classes. So C's, I've just called it here. And let's say that was the number k, this real number, this integer k. We also had the constraint that summing up the dimensions squared of all of these representations, irreducible representations, I should say, was equal to the order of the group. And what we've just shown by explicitly writing out all of these group elements is that there are 6 of them. Okay, so there are these 6 group elements in the permutation group. So we showed that this was 6, and as we showed, oh, thank you for the follow, whoever that was. Thank you for the follow, Bryce Allen. Very nice. We showed this was 6, and we, as we said earlier, we always have this trivial representation R0, which has dimension 1. So we've got 1 plus the dimensions of R1 squared plus the dimensions of R2 squared is 6, and that therefore told us that the dimension of R1 was 1 and the dimension of R2 was 2. Okay? So this is certainly the easiest next representation we can construct. Okay? It's one-dimensional, so the representation matrices are not really going to be matrices at all, they're just going to be numbers. Okay? And I think a trick we can use to construct this is one to say that the characters are the same for every element in a particular class. Okay. And the characters are just the trace of the representation matrices, and for 1D that just means they are the things themselves. Okay. So for G1, G2, and G3, the value of these things under this representation, so G1 in the R1 representation will be the same as G2 in the R1 representation, will be the same as the value of G3 in this representation, because they have the same characters, and the characters are just the representation matrices themselves in this 1D case. Okay. Another thing we can say is that we know that if something is a group, every element must have an inverse. So if we take a look at G1 and G2, G1 just corresponds to swapping around 1 and 2, and clearly the inverse of this, the thing that takes you back to the original arrangement 1, 2, 3, is if you just swap these things back. Okay, so in going from this line to this line, we've swapped 1 and 2, and if we want to go back, we just swap them again. Okay, so that tells us that G1, G2, and G3 are actually self-inverse. Okay, and in terms of the representation, because a representation is this group homomorphism, so it preserves the group structure, well, what this tells us, another way of writing this, is that G1 times G1 is E, and in terms of the representation, that just means RG1 times RG1 is RE, and RE is just 1. In a 1D representation, the identity is always just 1, okay, in order to preserve this group structure. So that means that in the R1 representation, the value of these group elements squared has got to be 1, okay? So in other words, the value of these things here have got to be plus or minus 1, and they all have to be equal to each other too, okay? And we just have to figure out whether they'll be 1 or whether they'll be minus 1, right? So R1 of GI is equal to plus or minus 1, where I is 1, 2, and 3 here. These are the first, second, and third elements of the group. So let's think about what happens when we combine G1 and G2. Let's multiply G1 and G2. Okay. So G1 means we are swapping 1 and 2. So we're taking 1 going to 2 and 2 going to 1. And G2 means we take 1 going to 3, so the thing in the first position, and the thing in the third position going to the first position. Okay, So we first swap 1 and 2. That's 1 goes to 2, 2 goes to 1. And then after that, we take whatever's here, goes to the third position, and whatever's here goes to the first position. So in other words, this goes like... Oh, hang on, I'm writing somewhere where you can't see, aren't I? It goes like... First it's 1, 2, 3. Then we end up swapping 1 and 2. So we have 2, 1, 3. And then we end up swapping 1 and 3. So we have 3, 2, 1. So this is our arrangement after doing G1, then G2, or G2, then G1, actually, it'll turn out to be. And what was it again? It was 3, 2, 1. And 3, 2, 1... Oh, hang on. Yeah, okay, that corresponds to G3. Is that correct? That doesn't seem right. I feel like these things should mix up differently. Wait, G1, G1, then G2. So that's 1 goes to 2. So then we get 2, 1, 3. Then 1 goes to 3. So that means we should have 3, 1, 2. That's not what I wrote down. No, we should have 3, 1, 2. Okay. So let me write that down again, what we did. Wait, where did I write it? Sorry, I'm dancing around a lot. I shouldn't be. So let's try again. So we started off with 1, 2, 3. That was the first one in the normal order. Then G1, this is swapping 1 and 2. So there we get 2, 1, 3. And then G2 is swapping 1 and 3 again. So now we swap 2 and 3. Okay, so that's swapping 2 and 3, 1 and 3, as in things in position 1 and things in position 3. So we actually get 3, 1, 2. Okay, not 3, 2, 1. Okay, and 3, 1, 2 is this element G4. Okay, the order does matter. Yes, absolutely. These are ordered permutations. Oh, as in, does the order matter of G1 times G2 or G2 times G1? Yes, in general, this is non-abelian. That's right. It will matter, yeah. So that gives us G4. G1 times G2 is G4. Okay. So thinking now in the R1 representation, when these things multiply together, so if we do R1 of G1 times R1 of G2, that should give us R1 of G4. And remember, these things here have to be the same. So they're either both -1 or both +1. And they have to combine to give this thing here. So that to me, probably need to justify that, but that to me makes me think that R1 of GI is equal to -1, where I is 1, 2, and 3, and R1 of GJ, where J is 4, 5, is equal to +1. Because actually R1 of G4 and G5 should also be either plus or -1. You can show. So G4, if you do G4 to itself again, so if you do G4 squared, that again gives you E. Okay, so here doing G4 once, we've taken 1 to 3, 2 to 1, and 3 to 2. And if we do the same thing again, so we take the thing in the first position to the third position, well, that means the 3 goes back to where it started, and then the thing in the third position to the thing in the second position, that means the 2 goes back to where it started, and the thing in the second position to the first position, the 1 goes back to where it started. So we again have a similar condition that R1 of G4, for example, squared should be 1. And the only way that is satisfied is if the R1s of G1, 2, and 3 are -1, and if the R1s of 4 and 5 are +1. Okay. So that means if we start drawing, we can start drawing out this character table. Okay, so we've got the trivial representation R0. We've got the dimension 1 representation R1, and we've got this unknown, so currently dimension 2 representation R2. Okay. And what we're going to do, so how do those plus minus ones relate to the characters? Well, they are the characters. And yeah, the table will show that. So because we're considering at the moment this one-dimensional representation, the character is just the trace of the representation matrix. And because this matrix is 1 by 1, it just means that the character is the thing itself. Okay, it is this one by 1 matrix. Okay, so looking at the characters, how should I draw this out? So these are the values of the characters for the first class, sorry, the 0th class, the first class, and the second class. Okay. Well, yeah, so the things I'm drawing in the table are the characters. Okay. So for the trivial representation, everything is mapped to 1. Therefore, all the characters are just 1. For this 1D representation we've just been thinking about, well, the identity element, the thing in this identity class, will always be 1 in this 1D representation. Then what we showed is that the things in the first class, which contained G1, G2, and G3, their representation matrix is just -1. Therefore, the trace of that 1 by 1 thing is just the thing itself. So their character is -1. And likewise for this second class, which has G4 and G5 in it, that will have a character of +1, as we wrote here. Okay. All right. Then for this 2-dimensional one, at the moment we don't know anything explicit about this. We don't know what these representation matrices look like. What we do know is that they're 2-dimensional, and therefore for the identity class, this element here has to correspond, the representation matrix of the identity element in this 2D representation will just be the 2D identity matrix. Okay, that'll always be the case. The identity matrix is something you can always fill in. The representation of the identity. So the trace of that, character being the trace of that matrix, will be 2. Yeah, exactly. Okay. Then these other things we don't actually know. We're going to call them A and B. But there's another useful fact. Yeah, it'll just be 2 inside the red box, exactly. There's another useful fact about characters, which is that characters, if you kind of make a vector out of them, they'll be orthogonal to each other, these irreducible representations. So, yes, exactly, orthogonality between rows. So if we take this inner product between the character of the 0 representation and what I called the 2 representation here, the 2D representation, that is equal to the sum over all the group elements of Well, these are all real, so it doesn't matter, but it'll be like the complex conjugative of this one here, and just this ordinary one here. Okay, so it's not just, we're not just multiplying the rows. We have to be careful of the fact that this class here has two group elements in. Sorry, this class here has one group element in. This class here has three group elements in, and this class here has two group elements in, because this is a sum over all of the group elements. Okay, so let's work out this inner product for the trivial representation and for the 2D representation. Okay, so for these first two elements, we just have a 1 times 2. Then for these two elements here, it's 1 times A, but there are 3 elements inside of this class. Okay, so that makes it plus 3 lots of 1 times A. And then for these two elements, now this class has 2 group elements in it, so it's 2 times 1 times B. Okay, and that should be 0, because these rows are orthogonal. Okay, the inner product of these characters, they form an orthogonal space. Okay, so that gives us one equation linking A and B, which we can rewrite as 3A plus 2B equals minus 2. Now let's do the inner product of R1 and R2, these characters. Okay, so it's the same thing here, just now we're doing it for 1 instead of 0. Okay, so these two elements, that's just 1 times 2. This will, 1 times 2 is the same, but it's that one. 1 times 2 plus 3 times minus 1 times A plus 2 times 1 times B. Okay, so now it's just 2 minus 3A plus 2B equals 0. Okay, or in other words, 2B minus 3A equals minus 2. So we have two simultaneous equations that are pretty trivially solvable, and we can find A and B. Is there an equivalent orthogonality between columns of the table? No, I don't think so. No, I don't think there's anything special about the columns of the table. Okay, so we can combine these equations. You can find that therefore B has got to be minus 2, I think, and A has got to be, is that right? It's got to be, no, B has got to be minus 1, sorry. And A has got to be 0. Okay. So that tells us the character table of this group. Now, we still don't know explicitly the 2D representation R2. We haven't explicitly found those matrices, but I think that wasn't the point of the question. The point was just to find the characters of it, and then you can figure it out. I suppose you've now got extra constraints. If you did want to explicitly find these 2D representation matrices, you can use the fact that the trace of the one that represents, or the ones that represent C1 is 0, and the trace of the ones that represent C2 has to be minus 1. But I think that's going to be a whole lot of other work to find the representation matrices explicitly. But I don't think that's what your question was looking for. So that was how I would find the character table using those properties. You've got quite strong dimensional constraints from this formula linking the dimension squared of the group to the dimension squared of the representations to the order of the group. Oh, good. Well, I'm glad you helped it. Okay, no, well, thank you very much. It was interesting. My group theory is not the best, but I'm glad you got something out of it. Thank you. So there was a question from Bryce. They said, "What do you think about into the future of science and technology years to come?" Well, I don't know. That's a very broad question. It's interesting. I saw a YouTube video just yesterday by, I can't remember the guy's name now, but he's quite a famous. He posts a lot of sciencey YouTube videos, and he posted one about. I think he made a prediction of what life would be like in 2020 when he was about 10 or something, or like 5 or 6 in about 30 years ago, and he was reading out his predictions. And then I did start thinking it would be nice for me to write down something about what I think the world will be like in 20 years. And I really was struggling to think about it. I didn't think about it too long. I don't know. It's so hard to think about these things technologically. I think when I think about how technology will be different in the future, in maybe the next 20 years or so, all of the differences seem very superficial to me. I think about differences in how information will be displayed and how we'll interact with technology, but not so much about the role it will play in our lives. Though I expect it will play a much more substantive role. I don't know exactly. I think things like wearable technology will probably become a lot more fashionable. And then I was really curious thinking about mobile phones, because think about what mobile phones looked like 20 years ago, and just how uncommon they were for everybody to be using, sort of regularly. And now how ubiquitous they are, absolutely everywhere. I don't know. I wonder if mobile phones will survive, or if there'll be some. I expect they will, because I think there's only so much you can do in terms of optimizing size. You wouldn't want anything too much smaller than a mobile phone, because you can already build devices that are, fairly powerful, that can fit on your wrist or something, but people still don't use them to browse the internet or for entertainment so much. And of course, you have things that are much, much larger, just like ordinary computers. But I think personally, I think the size of a mobile phone is pretty optimal as it is now. So I don't imagine the way things will adapt will change that much in terms of mobile phones. I don't know. There's so much that it's something you'd have to think about for quite a long time to comment on it properly. But it's an interesting question, but I'm not too sure. Theoretical Fizz follows up saying, "Do you think fusion will be successful?" Again, I really don't know. I think just from the fact that there are so many people that are still working on it is probably an indication that there's something to it. But it's not my field, so I have no idea how close anyone actually is to it. But I feel like it's one of those things that people have been saying for a long time. Oh, within the next 15 years, within the next 20 years, we will have cracked it, and that's quite a few years ago still. So I really don't know. I think fusion is not. It's not the be all and end all. There are so many other forms of renewable energy that are accessible at the moment. Wind power, solar power, even like hydrothermal stuff. I suppose depending where you are. I think some countries, some of these like quite volcanic nations get a lot of their energy from geothermal sources, but of course it's not very convenient if you live somewhere like the UK that isn't particularly geothermally active. Yeah, I really don't know about fusion. I don't know enough about it to comment on the realisticness of it. Other things in science, I don't know. like, I think it's unlikely we'll make too much more progress with things like quantum gravity and string theory. I think those things have sort of, the general impression I get reading things from the late 80s and the 90s was that everyone back then pretty much believed that string theory was gonna. There was a few things to work out, but within the next 10 years, it would have been more or less all ironed out, and everything would be fine. And of course, that didn't turn out to be the case. So I think now people are a little bit less hopeful about it in the very, very near future. So I'm also not too hopeful about that. Alan MD says, where can I get notes? So if you mean the notes from what I've been writing here, I will upload those onto my website. So if you go onto my website and go onto like the Twitch office hours bit, I will try and upload these as soon as I'm done talking through things. What is the big thing in theoretical physics these days? As in like the sort of the big, what do you mean, like the big ideas towards like quantum gravity, or I mean, string theory is still very fashionable. It's still very popular, and a lot of people that are working on it still think it's, I think, along the road to something. I mean, I'm not a string theorist, so don't take what I say to the bank. But I think people are probably less optimistic about the timescales over which these things will be done, and possibly about there are a lot more details we don't know about. I mean, something that's very fashionable at the moment in physics is this idea of holography, and the ADS-CFT duality. That's a very fashionable thing that sort of has come out of string theory, but seems to be applicable beyond string theory. Though I think most people that are working in it still think that the ultimate sort of quantum theory of gravity will be stringy. I mean, string theory does gives you a quantum theory of gravity, but I think one of the issues is it doesn't give you the quantum theory of gravity that corresponds to our universe. There's this enormous space of possible vacua in string theory that it doesn't seem particularly natural that you have so much choice over the vacuum for your theory. But yeah, string theory is still pretty fashionable, I think. But holography is still a very popular idea at the moment, and has been for the last 20 years or so. Well, not 20 years, more like, actually, yeah, 20 years. Yeah, it's an interesting question. Yeah, I don't know. What does everyone else think? What does everyone else think about string theory? I don't know if there are any string theorists listening. I'd be interested to hear what they think, because I'm certainly not a string theorist, or even anyone that's just has an idea about it. Let me know. Or what do you think as well? What do you think the world will be like in more like 20 years or something? How do you think technology or science will change in that time? Because I'm really not very sure at all. Oh, you've started reading Zweiback's book. Yeah, that is a very good book, actually. I think it's actually designed, I think it was taught as an undergraduate course at MIT. So it's supposed to be very readable. I've never really worked through it in fullest detail. I think when I was learning string theory last year, we used Polchinski's book and Witten's book. And Witten's book, well, there are a few of them, I suppose. There are 2 volumes, I think. Well, there may even be 3 volumes, I'm not sure, but I never even got to volume 2, so I don't know about volume 3 if it exists. But volume 1 of Green, Schwartz, and Witten's string theory book is quite clear. So yeah, I would recommend that, definitely. Yeah, though actually, I think Ed Witten. Yeah, it's that Ed Witten. What, if any, courses did you wish you already had started away when you began your PhD first year? I don't know really, because to be honest, I did quite a few courses during my master's year. I think I did, you know, if anything, I wish I had taken a few fewer courses so that I could have spent more time on them individually. You know, there is such a thing as taking too many courses and spreading yourself a little too thin. So there aren't particularly any that I wish I had taken that I hadn't already taken, but there are certainly some that I wish I had taken slightly more exclusively than I actually did in my masters. So so my masters year I did like 2 quantum field theory courses, a string theory course, GR courses, a cosmology course, an astroparticle physics course. I went to like a fluid dynamics course, a groups and representations course, applied complex analysis, perturbation methods, conformal field theory, and I think that was it. And I went to a little bit of QFT and curved spacetime, but I didn't do all of them. So it was a lot of courses, but there are still some things that are, you know, part of, say, like the group theory we're doing, things I forget just from normal group theory, and quantum field theory and stuff like that. So I think it would be nicer maybe to have taken it a little bit more slowly. I'm not the fastest learner, so it would have, you know, it would have been nicer to have gone a little bit slower perhaps, and had suspended, because especially because terms in Oxford are so short. We have 3 8-week terms, so I mean that's only 24 weeks to take however many courses that was, you know, which probably averages out like 2 weeks per course. And I mean it takes longer than 2 weeks to learn string theory, or to learn, you know, to learn these things in an interesting way. So it was pretty rushed. Did we cover all the prerequisites for those in my bachelor's? Sort of, yeah, I'd say so. I mean, yeah. You know, it's not like we started in the first term and I forgot as well. I also took a supersymmetry and supergravity course. I forgot that one. But what I was going to say is, it's not like in the first term we just dove in and started doing supergravity. You know, we first had a first term which was a lot of the groups and representations, and the quantum field theory and GR course, and stuff that was stuff you could follow on from, just from doing the first 3 years of the undergraduate course, any undergraduate physics course. But then it built on that. So then the second term we had some string theory and supersymmetry. So by then you'd picked up those prerequisites from the first term. But in terms of prerequisites for studying QFT, there aren't, you know, a standard sort of undergraduate physics education is enough prerequisite to be studying quantum field theory. I mean, you need, you know, sort of relativity, studying things like electromagnetism and knowing a bit about how gauges work and stuff like that. And then the kind of, classical field theory, exactly. And also sort of some of the mathematical technology like Fourier transforms and things like that. Of course you need as well, but it's all stuff you would pick up in a physics degree. And then, of course, the later terms of the course, it built on all of that. But it was a demanding course. But for those that are wondering, the course I did was it's called the M Math Phys course in Oxford. It's sort of similar to the Cambridge Part 3 Tripos, the maths course, in its sort of scope. Imperium 42 says, do you code for fun? No, not for fun. I sometimes do code for, because I have to work, and I do enjoy it to an extent, but it's not my favorite thing. I prefer to calculate for fun, or try and think about physics for fun rather than coding. But it's a very useful skill, of course, that, whatever field of physics you're in, pretty much now, you need to have some idea how to code and how to work these things. So I do enjoy it, but it's not It's not the reason I get up in the morning. What about you? Do you code for fun? Are you, you know, are you interested in that kind of thing? Oh yeah, I should. Oh yeah, Marmite pasta. I also forgot QM, of course. You do need to know some quantum mechanics too. You code for money. You're studying. You need a life. Ah, okay. Yeah, well, coding for money is definitely also good inspiration for coding. Okay. Yeah, that was an interesting question though about. I don't think there are any courses I wish I had taken. I mean, other than, it would have been nice to have taken some history courses or just general, I don't know, music courses or something. I think it's a shame that when you do a degree in the UK, you are very pigeonholed very early on. You know, we don't have a sort of year of like a general education requirement, which I think would be nice. No, I didn't take any language option. No. I am, as most British people, totally monolingual. um I wish I had. We learnt French in school a little bit, but I never actually learnt any French. The moment you're trying to play catch up since you feel like you started late, so I'm trying to cram as much physics in as possible. Yeah, there is a lot to learn. Yeah. I mean, it seems like you're doing pretty advanced stuff, though. You're doing, this group theory stuff and this QFT stuff. I think you were talking about last time. So, I think your knowledge is definitely pretty good if you're doing this sort of stuff. Oh, you've been in Sweden for 2 years. Ah, but you speak no Swedish, right? Yeah, that's a very British thing to do, to move to another country and not learn the language. British people are pretty bad at speaking other languages, I think, in general. We're not especially cultured in that way. Yeah, me too, I think. Okay, well, are there any other questions? We might wrap it up. If there's anything quick to go over. Did we get tutorials in year 4? Oh yeah, for my master's year, we did have sort of more like classes than tutorials, not like sort of three people and one professor. It was more like kind of 10 people and one TA or something. So not the sort of intimate, rather stressful, typical Oxford tutorials. More like standard classes, I think. They were good. Imperium 42 says Johnny tossed an apple on top of a 500-foot building in a 330-degree angle with a velocity of 40 miles per hour. What is the total surface area? Nice. The answer is 42 in units, where 1 unit is 1/42 of the total surface area of all the planets and stars in the Milky Way. Or it's 1 in natural units. There we go. Natural units of surface area of stars and planets. That's my answer. But I appreciate the question. Very funny. Okay, well, I think we will leave it there then. As I was saying to someone earlier, I will post these notes, the PDF, on my website if you want to take it out. Feel free to join my Discord if you fancy. Oh, why did it not come up? Okay, it doesn't seem to have... Oh, there we go. Right, it just took a minute. Okay, it worked. Yeah, feel free to join my Discord. And I'll be back tomorrow. So what day is today? Yeah, tomorrow evening. And we'll do some Mario Kart and chat some more about physics. So hopefully see some of you then. Okay, good to see you all. Bye, everyone. Bye.